All right, we're going to set up an RLC circuit today, and if you look at the lab handout on page 2, the circuit that we're setting up, we're going to take the output from the function generator here and run it first into an inductor, from there into a capacitor, and then finally into this resistance box, and then back, and then we'll have the oscilloscope channel. So I'm going to start by connecting the function generator to one side of the inductor to the capacitor, there to the resistor, and then finally the resistor back to the negative side of the function generator output. So I know this might be a little bit of a mess visually, but I just wanted to show you setting it up. And then what I'm going to do next is take my oscilloscope channels. The oscilloscope is just off screen, up there. And the first channel, channel 1, is going to be VO. And so that's going to be just the output of the function generator. I can do that on this cable over here. Just put in the red on the red and the black on the black. So now the oscilloscope is showing us the output of the function generator. And then for channel 2, I just want to look at the voltage across the resistor. I can actually just clip right into the back of these cables. Put in the black wire on the negative side. And so I've got the circuit set up, and what I'm going to do now is just kind of sweep through a set of frequencies and just qualitatively demonstrate the behavior of the circuit. So right now we've got 2 plots on screen. Channel 1 is the voltage output of the function generator, or the voltage across the entire circuit, and channel 2 is the voltage across the resistor. So that's going to be the one that's proportional to the current. So right now, channel 1 is the sine wave that you see, and channel 2, the voltage across the resistor, is very small. It's a sine wave as well, but it's very close to the time axis. So what I can do is start turning up the frequency, and I'm going to zoom in a few times as I do this. But you can see as I go up in frequency, if you're watching channel 2, that sine wave is starting to get larger in amplitude. And I'm going to stop here for a minute and just point out the phase shift. The current, which is represented by that smaller sine wave, you can see is ahead in time of the voltage. So, well, yeah, we'll come back around to that in a minute. But as I turn the frequency up, you can see that current is getting larger and larger. The voltage across the entire circuit is also getting smaller, but that just has to do with how much current is coming out of the function generator. So right about here, you can see they line up in time. So this is the resonance point of the circuit, where the voltage is in phase with the current, and the impedance of the inductor and the capacitor cancel out. If I keep going up in frequency, you can see that not only does the current get smaller, but it starts to lag the voltage across the circuit. So when we were at low frequency, the impedance was dominated by the capacitor, and now that we're at high frequency, the impedance is dominated by the inductor. Right now, the frequency that we're at is 2.57 or 2.58 kilohertz, depending on what it's jumping around to. The channel 1 voltage, which is the output of our function generator, that's going to be VO in the lab right up. So VO is channel 1, that's at about 8.5 volts or so. And then channel 2, which is VR, that's the voltage across the resistance box, is 2.72. So those three measurements, the frequency VO on channel 1 and VR on channel 2, are the three things we need from this screen. The other thing we need is the time offset between the waveforms. So if I go to time cursors and zoom in a little bit, I'm going to set up time cursors. And here what I'm going to do is put cursor 1 at the peak of VO waveform, and then put cursor 2 at the peak of VR waveform. So you can see there the delta is 76 microseconds. And so that would be the time delay between the signals. In this case, the current is behind the voltage, and so this would be a positive time delay. If I go down to a lower frequency, like say here, now the current is ahead of the voltage, and so this would be a negative time delay because the current rises first and then the voltage behind it. So that should be everything you need for measurements from the photos.